Thank you, Ruth, for organizing this and doing all this hard work. And I want to say it's my students who are starting the community garden. Good work. And if anybody wants to help with that community garden, the student team that's doing it can always use volunteers. So I want to thank all of the organizations that have supported our work in solar astrophysics over the last about 20 years. Do I have a pointer? Can you see this? Can you see that? Oh, great. Okay. The National Center for Atmospheric Research at the High Altitude Observatory in Boulder, Colorado, supported our work and the work of about a dozen Evergreen students studying the sun and its magnetic changes. The Solar and Astrophysics Laboratory at Lockheed Martin supported the work of 6 or 8 students, including one who's now a new professor at Evergreen, and NASA and the National Science Foundation and Evergreen have all contributed funding to our work. So thanks to all of our colleagues who have helped me learn solar astrophysics over the last couple decades. We'll learn some basics about the sun, and trying to see what you can see. And why does climate change? Partly because of the sun, also because of some other things. How does solar power change on Earth and why? Why do ice ages happen? And big question in everybody's mind. What about the Maunder Minimum? I get this question all the time. Did the little ice age happen because the sun got dimmer? And what's happening now, and why, and what's going to happen in the future. So we'll take a look at some of these things, and I know that you have questions, and I'm looking forward to your questions. We'll save time for that. So everybody knows that the sun is our major source of energy on Earth. It drives life and cycles on the planet. The gradients in heat, it's warmer near the equator and cooler near the poles, as Gerardo told us last quarter, causes the winds and circulation in the oceans. So the sun causes weather, and the sun causes flows in energy, in air, and in water, and in nutrients on the planet. So the sun drives life on the planet. Here's some ideas that people have about the sun. Let's see what your ideas are about the sun. It's warmer in summer, right? It's warmer in the northern hemisphere. So when is the sun closer to the Earth? When is the Earth closer to the sun? In July. Or is it in January? When is the sun closer? If it's warmer in the summer, is that because we're closer to the sun? That makes sense. And so a lot of people figured that we must be closer to the sun. And you see those pictures in your textbook of this really elongated orbit, right? But actually, we're closer to the sun in January. So if we're closer to the sun in January by a tiny bit, not even by very much, if we're closer to the sun in January, how come it's hotter here in the northern hemisphere in July? Ideas? I see some hands up. Tell me about it. Yes. Absolutely. It's because of the tilt, because in July, the northern hemisphere is tilted towards the sun, and then in January, the southern hemisphere is tilted towards the sun. Exactly, it's about the tilt. The distance doesn't make much difference. The Earth's orbit is so close to circular that you can hardly tell the difference between January and July. It's the tilt that makes the difference. Here's another idea about the sun. The sun goes through fluctuations. Sometimes it's got solar max, with sunspots and magnetic storms and coronal mass ejections that send extra particles and energy to the Earth. And so solar max does make the Earth a little bit warmer, and solar minimum makes the Earth a little bit colder. So do these magnetic fluctuations cause the ice ages? Here's something I got off the web. Maybe the fact that we're going through a minimum in solar magnetic activity right now, and that's true, we are. Does that mean we're going to have an ice age in your lifetime, in my lifetime, even though I'm old? We'll examine that. The sun, of course, is the main source of heat to the Earth. Does that mean it must be the cause of global warming? Here's another thing I found on the web. Friends of Science says the sun causes climate change, and they have this data that says the temperature changes are lined up exactly with the fluctuations in the sun's energy. Wow, what about that? We'll take a look at that. Okay. Here's another idea about the sun. The sun's getting hotter and hotter as it's turning into a red giant. Here's the sun now, and in a few billion years, the sun is going to get bigger and bigger and blow up into a red giant that will first encompass the Earth and then encompass the orbit of Mars. Wow. So, does that mean that whatever humans do is hopeless? Well, a few billion years is a long time. And we humans have only been around for a tiny fraction of that time. So what we have to do before the sun turns into a red giant, it matters. It matters to humans because we have a long time to go as humans before that happens. So what's the sun doing? Deep in the core of the sun is doing fusion, nuclear energy, not the kind that works in nuclear power plants right now, but it's turning hydrogen protons, the simplest form of matter, 4 hydrogens combine into 1 helium, and that releases energy, mostly in the form of massless photons, gamma radiation, and that energy makes its way out of the sun, and finally that massless radiation comes to Earth and heats up the Earth. Now it takes about 8 seconds for the energy to get to the Earth. Wait, is it 8 seconds or 8 minutes? It takes us minutes, 8 minutes for that radiation to get to Earth. So how long do you think it takes to get from the center of the sun out to the surface of the sun? It takes hundreds of thousands of years, up to close to 1 million years. Why does it take so long to get out of the center of the sun? It's just photons, it's just massless radiation. What could be slowing it down? It's traveling at the speed of light. Why does it take so long? Because the sun is so dense that every photon hits matter, gets absorbed and re-emitted, absorbed and re-emitted, absorbed and re-emitted. And so that photon gets blocked as it's trying to make its way out of the sun. And it has so many absorptions and re-emissions, or collisions, if you want to call them that it takes forever to get to the edge of the sun. Whoops. And then it zooms right out in 8 minutes to get to the Earth. So there are 2 processes that send energy to the sun. There's massless radiation, that sends the most of the energy. There are also coronal mass ejections. There are these big events when the sun goes through periods of magnetic activity, it has occasional burps of magnetized plasma, ionized gas. It'll send about 1 billion tons of magnetized gas to the Earth or out into the solar system. Every now and then, one of them will encounter Earth, and this billion-ton burp of magnetized plasma or coronal mass ejection will come out to the Earth. And mostly, it has little impact on the Earth because the magnetic field of the sun that's embedded in that plasma is deflected or protected by the Earth's magnetic field. The magnetosphere of the Earth will deflect that coronal mass ejection and it'll go around. Every now and then, the magnetic fields will be oriented such that the coronal mass ejection can partly penetrate the Earth's magnetic field. And when that happens, it will compress the Earth's magnetic field and cause a magnetic reconnection on the far end. That will send charged particles back toward the Earth, and that's when we get aurorae. That's when we get the light show. Those charged particles will excite the Earth's upper atmosphere and make them fluoresce. And that can also send magnetic storms to Earth. That's part of the process. So this can have impacts on Earth, but this is not climate change. It's an interesting phenomenon. It can affect satellites on Earth, but it does not affect climate. It can affect astronauts, but we now have the Space Weather Prediction Center that monitors space weather, monitors magnetic fields from the sun. And so when these events are happening, we tell the astronauts, go back inside the space, the ISS, and don't get hit by that radiation. So we have particles and we have mass coming from the sun. This has been happening forever. The Earth is used to it. It's not changing the Earth's magnetic field. So why does climate change? Well, you know, one big reason why climate changed recently, right? The meteorite that hit in the Yucatan Peninsula and changed Earth's atmosphere and killed the dinosaurs and a lot of other things. Volcanoes have had a big impact on climate in Earth's past. In the early Earth, volcanoes emitted greenhouse gases that warmed the Earth. In the present, they emit those same gases, but they're not enough to make a big difference. What makes a difference from volcanoes now is sulfuric acid and aerosols, which have a cooling effect on the Earth now. Life forms have changed the atmosphere. 3.5 billion years ago, the Earth was too cold was so cold that it should have been ice, but life forms were changing the atmosphere, and that had an impact. Blue-green algae, cyanobacteria, were creating oxygen, and that changed Earth's atmosphere. Other processes were also changing Earth's atmosphere, and there are life forms that are changing Earth's atmosphere now, and these things have impacts on climate. Solar power has also affected Earth's climate, and we know pretty well how that has happened for the last 2.5 million years, and I'm going to tell you more about that. It also depends on feedback cycles, which we'll talk a little bit about. So we can track ice ages back really pretty carefully for almost the last million years, and a little less carefully for the last 2.5 million years. And we know that through the last 2.5 million years, that is the Quaternary period, that the Earth's aspect to the sun has changed the amount of solar radiation the Earth has got, and that has been a primary driver of ice ages. So here's the present, and here, the blue, is the temperature. And every 100,000 years, we get a peak in temperature and then a dip, a peak in temperature and then a dip. This is an interglacial, and here's a glacial period. So here's a warm period, it doesn't last very long, and then the Earth gets glaciated. A sudden warming, and then a cooling, and a glaciation. About every 100,000 years, the Earth's orbit around the sun changes, and that allows the Earth to warm up. The sun's not changing, but the Earth's motion, or the Earth's tilt, is changing. We'll show you how. And notice that the red line is changing with the temperature, and that red line is the atmospheric carbon dioxide. Sometimes the carbon dioxide seems to increase a little before the temperature. If the carbon dioxide increases before the temperature, the carbon dioxide can cause an increase in temperature. Sometimes the temperature goes up first, and then the CO2 follows. These are linked. Greenhouse effect. You all learned in grade school that greenhouse effect can impact climate. This has been working on the Earth for billions of years in different forms. It's not a reflection of radiation, but an absorption and re-radiation of radiation. The sun's radiation is absorbed by the Earth, and then the Earth radiates a lower energy form of photons, infrared radiation. Some of the Earth's radiation gets out into space, some is absorbed by the atmosphere. And when we have more greenhouse gases in the atmosphere, they re-radiate more of that warmth that infrared back to Earth. So, why does solar power to Earth change? We've seen that changing solar power is one of many things that has changed climate in the past. Let's see why it changes. How does power from the sun change? There's a few things that can change solar power. Over billions of years, the sun is very slowly getting warmer. Over tens of thousands and hundreds of thousands of years, Earth's orbit changes. And that can change the amount of power we get from the sun. And on an even shorter time scale, over decades, the sun pulses. It has these magnetic cycles. I'll talk a little bit about each of those. First of all, over billions of years, the sun slowly gets warmer. This happens to all stars like our sun. In fact, this is known as the faint young sun paradox because way back when life was first starting, if you just look at the energy we were getting from the sun, Earth should have been totally frozen, but it wasn't. Why? Because there were volcanoes giving us greenhouse gases, and there were life forms changing Earth's atmosphere. And that allowed Earth to be above the freezing point, even though the sun wasn't warm enough. Why is the sun getting warmer as it ages? Because it does fusion. An aging sun heats up as it runs out of fuel. That seems paradoxical. If it's running out of fuel, how can it get hotter? As those 4 protons combine into one helium in the fusion process, the nuclear burning in the core of the sun, more particles turning into fewer particles. Remember back to your chemistry, PV equals nRT. If the sun has approximately constant pressure, then lower N, fewer particles, means higher T, higher temperature. It's just about that simple. So as the sun creates fewer particles running out of hydrogen fuel, it makes a higher temperature and turns into a red giant. Now, about every 100,000 years, the sun's orbit goes from pretty circular, the way it is now, to more elliptical. And that means that we get more extreme temperatures at the seasons. We can also have a changing tilt in our orbit, and our orbit can precess. These happen at different time scales. The combination of these changes in Earth's orbit can change our insolation, or the amount of sunlight we get. So our tilt can change a few degrees, and this happens over a time scale on the order of 20,000 years, on the order of 40,000 years. Our precession changes. We point at different stars on the order of a few tens of thousands of years. For example, right now, our orbit, the axis around which Earth spins is pointing at the North Star, Polaris, right? But in a few thousand years, we won't have a North Star because, like a spinning top, Earth will precess and we'll be pointing to an empty spot in the sky. A few thousand years ago, we were pointing at a different North Star, pretty close to a star in Draco the Dragon. It's a different constellation. And the biggest effect is due to Earth's changing eccentricity. Right now, Earth has a pretty circular orbit. That is, we don't see a big difference between summer and winter, but sometimes we have a greater eccentricity. This is exaggerated, but every 100,000 years, we get a more elongated orbit, and that has a big impact on climate. So if you look at the amount of insolation or power from the sun that we get over hundreds of thousands of years, you can see that we get big changes due to our changing eccentricity, tilt, and a combination of tilt and precession. If you add it all up, you see that we get peaks in our total power from the sun at a northern latitude. This matters because this is where ice ages form. This is where ice ages like to start, at a northern latitude. And there's a little bit of a correlation. Here's a peak in our insolation, and here is, we're getting more sun, and here we're getting a warm period. These benthic forems, these Plankton deep in the ocean that can be measured in ice cores are showing there was a high temperature at a time when we had a lot of sun. Here was more sun and a high temperature, more sun and a high temperature. There's kind of a correlation. It's not perfect because we also need feedbacks. So let's look at what's happening with this Milankovitch mechanism, this combination of all these changes in Earth's orbit. There we go. This one here. I got the sound turned off, and I'm just going to explain what's happening. So here's the Earth going around the sun. This part is exaggerated. Oh, you can't see it? Uh-oh. How do we fix that? How can we make this visible? I need some technical assistance here. Andre knows how to fix it. Yay, Andre.
Oh, I got a round of applause. That's special.
Hey, thank you. Okay, great. All right, so here's the Earth going around the sun, and uh-oh, thank you. You guys know YouTube better than I do. All right, here's the Earth going around the sun. Great. And I'm gonna drag this forward. Earth going around the sun. Okay, so here's the Earth going around the sun, and here's the sun moving through the constellations. This happens through the course of a year right now. You can see the Earth going through the constellations, except, of course, you can't see those constellations during the daytime. Let's drag this forward a little more. And, whoops. Thanks for the ads. All right. We're going to move this forward to, there we go. All right. So here's the Earth. Precessing and spinning around the sun. There we go. Wait a minute. Let's get to the good part. Where's the good part? Let's get to the good part. Wait, is this the wrong one? Oh, heck. Gosh darn it. Wait a minute. Did I get to the wrong one? This is it. There we go. Oh, all right. Sorry. All right. Try this again. All right. This is it. All right. Sorry. Oh, sorry. Okay. So the Earth's going around the sun, and it's pointing always at the North Pole. It's spinning from day to day. It's moving around the sun throughout the year, and it's always pointing at the North Pole. I know you saw this in grade school, but it's going to change because we're going to advance tens of thousands of years. All right, still pointing at the North Pole as it goes. So here's the summer solstice. Here's January, because we're closer. It's not this elliptical. It's really very circular. This is exaggerated. All right, so now we're going to have an exaggerated change. Let it go ahead. I'm not going to play with it. I'm going to let it do its thing. Maybe I will play with it. There we go. Right now, it is pretty nearly circular. So that very elliptical orbit you saw will be in the future and has been in the past. Right now, the Earth's orbit is really close to circular. It's just a tiny bit further away in January. And the Earth's tilt angle changes. Right now, it's 23.5 degrees. And when it's less, then there's less extremes in the seasons and less melting. And when it tilts more, we can get more melting. There we go. And the North Pole, and as we precess like a top, we can get a new North Star, or most of the time, no North Star at all. So right now, as you know, our northern hemisphere is close to the sun our northern hemisphere is close to the sun in June. What? Okay, we're going to stop this. There we go. So that's how Earth's cycles change, and the ellipticity of the cycle is the biggest change. What? Can you see this now? Great. Okay. So the changing eccentricity or ellipticity has the biggest impact. So if we sum it all up, we can see how the changes in the radiation from the sun due to Earth's orbit correlate with the carbon dioxide and with the temperature and with the sea level. So this is the biggest impact on Earth's climate in the past. But notice what's happening right now. Right now, Earth has a really circular orbit, and the Earth's and the insolation we're getting from the sun is really low. We're really at a low point in insolation, but the CO2 is really high. The sea surface temperature is really high, Antarctic temperature is really high, and sea level is high. So the sun is not driving the high temperatures and the high CO2 and the high sea level. Something else is doing it. It's not the sun. Usually it's the sun. It's not now. It's not the increase in solar power due to Earth's orbit. We'll get to what that is. You already have an idea. There's another thing that happens. The Earth has changes on... Oh, same thing. Let me see. I'm not going to remember how to do this. Will you show us again? Oops. Better go back. There. Do your clever thing again, Andre, please. Ah, it was hidden. That's it. Yay.
Oh my God.
Yay, Andre. Okay. Stay away from that.
When we look up at the sun from Earth, it seems calm and unchanging. The truth is quite different. In addition to these abrupt changes in activity, the sun also has a long-term, more regular pattern of change. This pattern is called the sunspot cycle, and a single cycle lasts for about 11 years, although it can be as short as 8 or as long as 14, and it can vary dramatically in intensity. During one cycle, the number of sunspots, a good indicator of solar activity, goes from low to high and back down to low. Solar minimum represents a period of time when sunspot numbers are relatively low, and solar maximum represents a period when sunspot numbers are relatively high. During this cycle, the location of the sunspots also changes. They are at middle latitudes during solar maximum and move closer to the equator as the sun approaches solar minimum. At solar minimum, there are sometimes no sunspots to observe. At solar maximum, there can be many at the same time. The number of sunspots is important because sunspots are the visual markers of where powerful magnetic fields have emerged from the sun's interior. These magnetic fields power solar flares and coronal mass ejections, which can affect Earth and other objects in the solar system. As the sunspots increase, so does the frequency and severity of flares and CMEs. The sun's 11-year cycle is a symptom of a longer 22-year cycle called the solar cycle, or Hale cycle, which affects the sun's magnetic fields. Every 11 years, the sun's poles flip. North becomes south and south.
It's not that simple.
So every 22 years, return to the position where they started the cycle. The flip is due to the complex movement of magnetic fields inside the sun that are constantly stretching, twisting, and crossing as solar material bubbles up from the sun's core, but the exact pattern of movements is not yet mapped out. Because the sunspot cycle follows a similar pattern regardless of the orientation of the poles, it only takes half as long as the solar cycle. The two cycles are different, but the 11-year sunspot cycle is often referred to as the solar cycle, which can be a little confusing. Right now, the sun is approaching solar maximum, so flares and CMEs are more common than they were a few years ago. This cycle may peak in 2013 or early 2014, and should reach its minimum around 2020, although predictions about the sun are still uncertain. The slower than expected progress of this sunspot cycle has led some to speculate that the next sunspot cycle might be very minimal, with few sunspots even at solar maximum. It is still far too early to know, but even if this is the case, it has happened before and isn't something to worry about. It just means that the sun would briefly be a little closer to the unchanging orb it looks like from the ground.
Great, I like that. They did a good job. Okay. Can you see that? Okay. Got it? Okay, good, great. Okay. So our last solar max was really weak, and our next one is shaping up to be weak. We had a long, low solar cycle, and it looks like we may be in a Gleisberg minimum, which is an 85-year cycle of of minima. The sun has these decadal max and min, and we also have longer cycles of magnetic minima. And so what effect do those have on climate? Here's this 11-year cycle, and how does the sun's output change during these cycles? This has been blown up. There are a lot of solar observatories, mostly satellites, detecting how much radiation output the sun is giving, and they've been going back for decades, and they've all gotten calibrated so that they match. And we can see, it looks like a lot of variability from the sun that's correlated with the sunspot activity. But look at the scale here. They're all centered on about 1362 watts per square meter, and they're varying less than 0.1%. It's a tiny variation. It's such a tiny variation that historically this has been called, the output of the sun has been called the solar constant. This variation was unmeasurable until recently, now that we have satellites that can measure very, very precisely. In fact, you can see a lot of fluctuation in the measurements. The fluctuations are huge. So why do ice ages happen? Let's see. Here is the fluctuation in the output of the sun received by the Earth over hundreds of thousands of years due to Earth's motion around the sun. Here is the temperature change, a warm period, glaciation, warm period, glaciation. Here's the CO2. We got kind of a correlation going here. Which comes first, the chicken or the egg? Well, here's a warm period that was, here's a time when we had a lot of solar insolation, but it stayed glaciated. We don't have perfect lineup. Like it was warmer here than here, but there was more solar power here than here, but this is when we came out of that ice age. We do see a pretty close correlation between temperature and CO2. Sometimes one leads, sometimes the other leads. What's causing what and why? And what's happening now? We're at a really low solar insolation, high CO2, high temperature. So what's going on? Feedback mechanisms are really important. Some of you know about feedback mechanisms. They can either be positive or negative. Positive means they're self-reinforcing. Negative means they're stabilizing. Positive drives out of equilibrium, and negative drives a system back to equilibrium. For example, you can have a positive feedback that drives a system colder. You can have a change in the Earth, for example, more Earth being exposed. It causes a little bit of cooling, maybe some ice starts forming, and that starts breaking up the rock, and that absorbs CO2 and makes it even colder. There's a positive cooling feedback. You could also have a negative cooling feedback that would stabilize the Earth system. Maybe it starts getting colder, but then that decreases precipitation, which reduces the breakup of rock, and so there's less CO2 absorbed by rock, less weathering. That reduces the cooling, and you have a stabilization of the climate system. You could have a negative feedback, a negative warming feedback. Maybe it starts to get warmer, but that makes it rain more, and so that increases weathering, and the rock absorbs more CO2, and that reduces the warming. That's stabilizing. Or you could have a positive warming feedback. It starts to get warmer, you get more water vapor in the air. The water vapor is a greenhouse gas, that makes it warmer. That's going on right now, a positive warming feedback. These feedbacks like these are critical for determining whether something like increased insolation due to changes in the Earth's motion drive the Earth in or out of a glaciation. So what about the Little Ice Age? Did it happen because of a solar magnetic minimum? This is something that's out there on the web. A lot of people talk about it. The Thames froze in the 1600s, and there were no sunspots. Galileo had just invented the telescope around he had appropriated the design of the telescope from a Dutch lens maker and made it popular, made a lot of money from it, made some money from it. Anyhow, everybody was observing sunspots. It was a fad, and they disappeared. And it got cold, and they said, oh boy, maybe there's a correlation. But first of all, which Little Ice Age are we talking about? Well, there was the Maunder Minimum from 1645 to 1715. There was a dearth of sunspots. There was a growth in ice. And what was happening with the total solar irradiance? Well, it had been, fluctuating, but kind of steady. There was a little dip at the beginning of the Maunder Minimum, but here there's still no sunspots. But we had some more solar irradiance, and the solar irradiance was coming up even when there was continuous ice cover in the northern hemisphere, all the way into the 1700s on the northern ice cap. So it's not clear. Here we have continuous ice cover in the North Pole, even though we've got solar irradiance coming back. So what's going on? An important thing that's going on is volcanoes. There were major volcanic events that went on right before the Little Ice Age happened. 3 major volcanic events, and then another one right before we got this big onset of ice cover. Volcanic events are significant in this epoch for sulfuric acid and for aerosols, which reduce the warming of the Earth. Or is this the Little Ice Age we're talking about? The Middle Ages started cooling from about 1300 on. There were 3 grand solar minima. 2 of them were even deeper than the Maunder Minimum, and there were even more bigger volcanoes. Crops failed, there were plagues, and people fought. Millions of people died in wars. And what was going on with the rest of the world? Major volcanoes. Here's the volcanic record from modern data. We can connect it back to 2 other data records. All these data records match, and if we go into the paleo record for volcanoes, we see major volcanoes right before The major ice ages set in around 1300. So the net radiative forcing, that is how much is energy moving the Earth away from equilibrium, starts going negative in a big way. So volcanoes are having a huge impact in the ice ages, from the Middle Ages all the way through to the Maunder Minimum. Or do you mean by little ice age the one that happened most recently? You know that just about 12,000 years ago, we were coming out of this ice age. It was starting to warm, and then boom, there was a sudden refreezing. The younger Dryas is named after the reappearance of these flowers that are found in Europe. We can see that there was this big temperature drop. We were starting to warm out of the last glaciation, and then boom, we got a freeze. What was happening then? There was a freshwater influx as Greenland started to melt. That freshwater influx changed the thermohaline circulation of the ocean in the North Atlantic. It decreased the warm water that was coming up from the tropics and caused the Northern Europe to freeze again. Is that the little ice age we mean? That was not due to a change in solar insolation. And people are afraid that might be happening now because Greenland's melting again. So could global warming, which is melting Greenland, cause another ice age? That's what happened in the day after tomorrow. Oh no. Could global warming be causing another ice age? Let's see what's happening now. Greenland is melting. The North Atlantic thermohaline cycle is weakening. And we've had 3 major volcanoes in this past century. So those volcanoes have, in fact, saved us from 1 degree C of global warming. You know that we've had a 1 degree C increase in global warming in the last century. It would have been 2 if we hadn't had those volcanoes. Northern summer insolation is at a minimum right now, as we've seen. So Earth should be starting to glaciate. We should be expecting a glaciation right now. What's going on? Why is it getting warmer? Okay, here's the sun. Sunspot number is kind of correlated with the insolation. Temperatures going up, CO2 going up. They always go up together, no matter what the sun does, no matter what the Earth's orbit does. What is forcing Earth's climate? This is in the article you read for today by Dr. Judith Lean. So solar irradiance varies. Every 10 years, we know that a tiny bit, a fraction of a percent. Volcanoes, boom, boom, depress the temperature, depress the forcing, depress the Earth, move Earth away from equilibrium in a cold way. El Nino has a big impact. El Nino Southern Oscillation is a weather pattern, but it can have a measurable influence. Let's look at the data. Surface temperature has been fluctuating. You can see the depressions from the volcanoes. You can see some of these peaks from El Nino. Can you see the oscillations from the sun? I don't know, they're kind of small, but you can definitely see a steady increase, and that is from increasing carbon greenhouse gases, CO2 in particular. Solar radiation reaching the Earth, there's a lot of it, but it's mostly in really long wavelengths, low energy. The high energy solar radiation, ultraviolet and higher, there's not a lot of energy in that. Somebody asked before this talk, wow, there's some really hot, there's a lot of temperature increase in the thermosphere, the very upper layer of the Earth's atmosphere. However, that's very thin. It has very few particles per square meter. And down in the troposphere, where Earth's weather happens, it's very low energy radiation. So what's happening, as you know, from the readings we did and the talks you heard last week with the climate change conference, carbon dioxide emission rates are increasing. This is our business as usual path. This is burning all the fossil fuels. This is where we're at about now. This is the end of the century. This is the Birkenstock model. If we do everything we reasonably can to reduce our carbon emission rates. This is a fantasy. This would be really nice, but it's not likely. If we really, really try hard, we could do this. Get our carbon emission rates down below where they were long time ago. So what happens to carbon concentrations if we do the Birkenstock model or if we do the business as usual model? If we do the Birkenstock model, by the end of the century, we can hope to keep carbon CO2 equivalent. Right now, it's about 400 parts per million. By the end of the century, we could hope to keep it down to about 600 parts per million. That's the Birkenstock model. Switch to renewable energy, plant lots of forests, share all our technology with the whole world, and make sure that all the women in the world are highly educated and have access to birth control. Business as usual, burn all the fossil fuels, we're over 1,200 parts per million carbon. Okay, those are our options. What are the consequences? As you saw in the readings and talks from last week, CO2 and other greenhouse gases are pushing Earth away from thermal equilibrium. They're driving Earth to a hotter state. They are the main activity that's pushing Earth toward a warmer place. Here's the sun. Here's the effect of the sun. Energy changes from the sun have a tiny effect. They have the uncertainty in the sun's impacts are smaller than the measured effect of the sun. Here's aerosols, black carbon, that's from fossil fuels, coals, wood burning warms the earth. Aerosols from volcanoes cool the earth. What's going to happen next? Well, we know what humans are doing with carbon. Here's our options. How will insulation change? How will greenhouse gases change? And will we have another ice age? This cool article came out just last week in Nature by Ganapalski et al., January 14th in Nature. Critical insulation CO2 relation for diagnosing past and future glacial inception. Here are 3 epochs of the Earth's orbit around the sun, and the green is now, and the other 2 are similar periods, 400,000 and 800,000 years ago. And here's time over hundreds of thousands of years. So we can see now, here's now, and the green line says that our eccentricity is going to be going down, which means we're getting more circular. Earth's orbit is getting more circular, which means that it's not going to be getting warmer due to Earth's orbit around the sun. Here's precession, here's obliquity, so that's the top motion of the sun, and here's the tilt motion of the sun. Here is what's happening with CO2. In past epochs, the CO2, when it was coming down, at these times, when the Earth's orbit was behaving like this, in our epoch, CO2 is at 280 parts per million. No, our CO2 doesn't fit on this scale. Right now, our CO2 is up here at 400, and it is going towards 1,000 parts per million. So everything else looks the same as these other 2 epochs, where we saw a decreasing CO2 and, of course, a decreasing temperature going into a glaciation. That's not what our epoch looks like. Even though the Earth's motion around the sun looks the same, our temperature in CO2 doesn't look the same. In fact, one of the conclusions from this article is that our current glaciation that we should be having now was prevented before the industrial era started, that our CO2 levels were already too high before the industrial era because of human impacts, agriculture, land use, and burning. We already had too much CO2 in our atmosphere to get into glaciation. At 240 parts per million, we might have made it. At 280 parts per million, we couldn't. Not with our orbit the way it is. That's an interesting result. That says something about when we might consider the Anthropocene having started. So they did a study of lots of epochs to find out how high your CO2 can be, and you can still get a glaciation. And if your sun is too dim, if you have a dim sun, there's a dim sun. If your sun is too dim, you're not going to get a glaciation. I mean, if you have too high a CO2, even a dim sun is not going to give you a glaciation. That's where we're at. So is glaciation possible in our future? So here is CO2. Here is ice volume, and here is, how much CO2 do we say we were going to put into the atmosphere? Over 1,000 gigatons of carbon. If we stop right now, if we stop emitting CO2 right now, let's say we stop at 1,000 gigatons CO2, will we get to a glaciation? Nope. If we stop at 500 gigatons, I don't know if we can do that, because even if we stop, what about the Earth's feedbacks? We have methane being emitted from the warming tundra and permafrost and from melting methane clathrates. So I don't know, even if we stop emitting, will the Earth stop emitting? What about those feedbacks? So it's not clear we'll be able to get to a glaciation in the future, even if we stop emitting CO2 right now. If we stop CO2 emissions at 1,000 or 500 gigatons of carbon, what would the ice volumes look in 20,000 years from now, in 40,000 years from now, in 100,000 years from now? Here's what the sun's going to be doing. It's going to be feeble. We're not going to have a lot of extrasolar insolation. That's not enough to put us over the edge. So if we have zero, absolutely zero carbon emissions, maybe? Could we get another glaciation? The conclusion of this article is that probably not another glaciation in the foreseeable future. So good times in the Pacific Northwest, maybe not so good in eastern Washington and other parts of the planet. Judith Lean reminds us that when the sun's fluctuating on its decadal cycle, it only warms the Earth a fraction of a degree. It only increases its output a fraction of a %. And this new article in Nature concludes that anthropogenic interference will make the initiation of the next ice age impossible over a period comparable to the duration of previous glacial cycles. But challenges like global warming also give us opportunities. And one of those opportunities is a transition to more renewable power, such as the solar power on the farmer's market. So we're moving to a new planet, and in some ways, a better planet. We will have, as you learned last week, an extended growing season in the Pacific Northwest. We have opportunities to do more of our own food growing here. And one of the opportunities that we have from these challenges is to come together as a community in new ways and in better ways to make a better life for ourselves and for broader communities around the world. Thank you.